This is Embedded Systems Design class, and today we will talk about LCD module interface. Last time we talked about the GPIOs, and we said that we have port A and port P with a specific number of bits, and we can configure them as inputs or outputs. Now, let's say that you have a very simple system and you want to output a message in a small screen. In that case, LCD is a good choice for you. And this is what we are going to discuss today. The LCD, which is the liquid crystal display, the liquid crystal is a compound that can polarize any light passing through it. The alignment of the LC can be changed by electric field, so you need a voltage source, and thus the direction of the polarization is changed. The LCD display is formed with a liquid crystal material sandwiched between two glass plates with transparent electrode patterns and polarizers stationed on the outside of the two glass plate. To understand this better, here is a small figure. So you have the light coming here. Now you can see that there are two glasses and what we call the polarizers, and the liquid crystal is in between. And depending on the light, the direction of the light and how it's emitted, it could be going directly or curved in such a way. And based on this, you can make some pixel emit certain light, other pixel will be kind of off, and so on. That's the idea behind the liquid crystal display. Now, if you have a small LCD, it's going to be one of these three types. Either it's going to be 7-segment or 16-segment or alphanumeric or graphic. This is the 7-segment. As you can see, if you count the number of segments, you'll find there are 7. And you can display the numbers, some of the letters using the 7-segment. The 16 segments give you more freedom. Well, for example, you can show the letter Z easily, while in the 7-segment, it's not going to be that, it won't look good. That's for the 16 segments. Now, the alphanumeric is pixel-based. So you have a certain number of pixels with a certain dimension. And as you can see here, we can show the number 8 with good clarity. Now, there are so many ways to categorize different LCDs. That's one way of doing it, which is the organization. Another way is the coloring. Some of them are colored, some of them are black and white. Also, the lighting. Some of them are transmissive, some are reflective or transflective. The transmissive require the light from the back, like the BC LCD. So if this is your eye, the light source is coming from the back, and then it's transmitted through to your eye. The reflective, there is an external source, lightning, that can work in sunlight, and it consumes less power. And this is the idea behind it. There will be a source somewhere. So there will be kind of a reflector, a mirror. So you have the light source, and it reflects back to your eye. The transflective have both of them. So either the source is going to be from the back, or it could be reflected back. Also, there's another way of categorizing the LCD using the refreshing or the refresh rate. We have the passive matrix display, which is the PMD. It's the pixel is activated by selecting its row and column. Also, you have the active matrix display, the AMD, which use a thin film transistor or the TFT. it is actually added to each pixel to improve the performance of the PMD, and this is why we call it active matrix display. Now, the LCD module, when we say the LCD module, the LCD with the driver, we mean that it is the LCD, the screen itself, with the driver circuit or the hardware that's behind the LCD. Obviously, it controls the state of every pixel through scanning and provide interface within the processor. So it's the screen and the hardware behind it. And of course, you need to program it. As we said, for each module, from now on, we need to make a good interface, or we need to make the interface in a right way. And also we need to do some programming. So here's some example that you might have studied in a digital design course, which is the BCD to 7-segment LED display decoder circuit. You have a 7-segment. The segments are called A, B, C, D, E, F, and then G. And there is actually a small chip that has a ground and it has a VDD, and it has A, B, C, D, E, F, and G. So the idea here, if you have the numbers, and we said BCD, that's the binary code decimal. So we have decimal numbers from 0 to 9. The display pattern should be this way. So the 0, you should light all the segments except the G. For 1, you only light B and C, and so on for each one of the digits. If you follow this, you can generate the truth table to design the hardware. So for these decimal numbers, if you put them in binary, you could put them this way. And the outputs will be as we expected. For example, for 0, all of them will be 1, except for G, it's going to be 0. For 1, all of them will be 0, except B and C, they will be on, which is 1 and 1, and so on. I'll give you another example. Let's say, for example, 5. So for the number 5, which is 101 in binary, the output should be all of them are emitting lights except the 2 segments here. This segment is B and this segment is E. So you can find that B and E is equal to 0. Now, once you have the outputs, you can get every column. There are 7 columns because we have 7 segments. So you can get every column and you put it in a K-map or a Carnot map, and then minimize or get the function for each column by using the K-map. And you know that K-map is actually minimizing or optimizing the design. Notice that the inputs is actually from 0 all the way to 9 only. So 10, 11, 12, 13, 14, and 15, we will assume that they are all don't care. So when we fill the K-map, like what you see here, you can find don't care for each one of the columns. That's for column A, P, C, D, E, F, and G. I'm not going through all the details here. I have another set of videos for the digital design class, so you can go and check how we use the Carnot map to get the function for each one of them. Once we get the functions, you can see that some of the terms are repeated, like the A, like the BC bar, like the B bar, D bar. You can see that it appears in many of the segment functions. Similarly, for the C, D bar or the C bar, D bar, there is certain repetition. If you are aware of this, you can make the hardware easier in design. So I rewrite the same functions that we got here, and then I build the hardware based on these. I'll just take one example, like for example, bPAR-C. You can see that bPAR-C, which is this one, you get it from bPAR. This is the bPAR input, and this is the C input. And then the bPAR-C term is actually one of the terms for D and also for G. And this is why you can see that there is a connection to D and also to G. And then once you get the output for each one of the segments, you can see that this design is actually AND followed by OR. So the last gate and before you get the function is OR for each one of the segment functions. And then you connect it to the appropriate segment. And now, if you put the inputs in binary, you can generate the letter the way you expect. Now, this region is considered one part of the LCD screen, while the hardware or the driver behind it is actually what you see here. Assuming we are doing a 7-segment LED display circuit. If we have 16-segment or alphanumeric, it's another story. But for this one, now if we enter 0, 0, 0, 0, this is going to be the output. And this is for 1, for 2, for 3, 4, 5, 6, 7, 8, and then 9. And that's the requirement for our circuit. It's actually a BCD to 7 segments. So it shows you the number from 0 to 9. So that's the idea of the LCD and how to build its driver. Now, what we want to do in this class is how to connect our microcontroller to an LCD and show certain letters or message, if you like to see. So the LCD module, there are so many types of LCDs. You can go to the market and you will see so many of them. And since you have many LCDs, each one of them will have its own data sheet. For what we will or what the LCD that we chose for this lecture is this is its name. The LCM is 01602 DTR-M. This is the LCD. So you can go search for it, get its data sheet if you like. But the important details, I already put it here in this slide. So this LCD has 2 lines, and each line has 16 characters. If you take one of the lines, or sorry, one of the characters in a specific line, the first line, you can find that this is actually alphanumeric with 5 times 8 pixels. So the total is 40 dots or 40 pixels. Now, how to interface our BIC24 microcontroller to this LCD? We need to know the pins of the LCD. We already know the BIC24, and we discussed this in the last lecture. But what about the LCD? What are these numbers? So you have the table here. You have the pin numbers from 1 to 14. You might see here that we have 15 and 16, but the 15 and 16 for this specific LCD is not used. For actually other LCDs, they might be used for backlight, anode and cathode in some of them. So here we don't use them. We have only from 1 to 14. 1 is the ground, 2 is the power supply, usually it's 5 volt. 3 is the contrast control, or what we call VEE, And you can see here that it is actually a variable resistance, where you change this variable resistance, and based on the change, the density of the light will be affected of the LCD. So if you want the character to show more clearly, you should reduce this resistance. Now, that's for 1, 2, and 3, and it's connected here. You can see that 1 is connected to 0 volt, 2 is connected to 5 volt, and 3 is connected to the variable resistance. Now, 4, 5, and 6, they are the control bits. 4 is the RS, set and reset, and it's very important to understand that here, if you have the value equal to 0, it means that you have an instruction input. If it is 1, then it is a data. So you might see that it's called set and reset, but the meaning behind it is kind of a little bit different. So from now on, for bit number 4, we would say that it is the control bit that's responsible for telling me, am I expecting an instruction or a data? If it's an instruction, if it is of the bit of that bit is 0, or if it is 1, then it is data. For 5, it's read/write, and that's as we expected. If it is 0, then you are writing to the LCD. If it is 1, then you are reading from the LCD. Now, you might think, this is an LCD, so I should give it character to show it in the screen. I'm always writing to it. Why do I need to read back? Sometimes we need to read back from the LCD. So my estimation, maybe 95 or maybe a little bit more, 95% of the time, you are writing to the LCD, and there is a small percentage you are reading back for testing purposes, maybe debugging, things like that. So sometimes you need to read the LCD. For bin number 6, this is for the enable. That's the enable. And you can see that 4, 5, and 6, which is this 4, 5, and 6, they are connected to the microcontroller. And I chose RP4, 5, and 6 for them. I could have chosen anything, but just to match the same bin in the LCD, I chose the same ones here. So now I need to program BIC24 to send what the LCD wants. If I want to write, I should send here 0. So write is the active low signal here. So I send 0 here. If it is an instruction, then it should be 0. If it is a data, it should be 1. And the BIC24 is responsible for feeding you these controls. Obviously, the same thing for the enable. Now, the rest of the bins from 7 to 14, that's for the data bus lines from 0 all the way to 7. So you have from 7 to 14, that's DB0 all the way to DB7, and you just connect them directly to the LCD. So you can see you can say that interfacing the LCD is fairly easy. Also, remember, this is for our own choice. This is for our own LCD. If you have another LCD, maybe some of the LCDs, they don't have 2 lines. They might have more than 2 lines, maybe 10 lines or 12 lines. So they have their own connectivity. But usually, most of these LCDs have 16 bits, and they are kind of the same thing. So now to understand how to program the LCD, how to work with it, we need to understand what is the capability that this LCD comes with. So we have the LCD controller behind the hardware behind it. It has registers. One of them is the data registers. The data register used to store the character to be displayed on the screen. And we have also an instruction registers. Instructions. You are giving instruction to LCDs. What kind of instructions? There are so many. some of them, clearing the display, homing the cursor, turning the display on and off, turning the cursor on and off, setting the display character to blink. So if you want a blinking message, you do that using this instruction. Shifting the cursor and the display left to right or right to left. And you can see this maybe if you go outside and you see while you are driving your car, some of the smart LCDs, they are actually kind of big screens. They are displaying messages that are shifted from left to right or from right to left. Also, you have reading and writing data to the character generator and to display it, these as the important command. And usually it's writing. I should give the instruction to the LCD, hey, write this data to the screen. More than that, we have the display data RAM or the DDRAM. It's used to store the LCD characters. And each character is stored as an 8-bit number. So it's 8-bit number. For example, if the character 0, if you want to show it, you should store it as 0x03. It's something like the ASCII code. And we will see how we get this number in the next slide. We also have the character generator ROM or the CG ROM. The ROM that has the bitmaps for each character. So the bitmap for character tells the LCD controller how to draw the character. Now each character in this bitmap is 5 by 8. And this is what we talked about when we said that each character is showing 8 times 4, 5 times 8, which is 40 dots. That's what we mean by that. So that's each character. So 5 bytes is needed to store a bitmap for a character. You have 8 bits, that's 1 byte, and 5 times 8, it means that it is 5 bytes. Now, how we get the 0? If we want to write down a 0 or a 1 or a character A, B, C, or any other character, how to find its corresponding 8-bit number, and how to find that in the CG ROM. You can see it from this character set. You have a low order nibble and a high order nibble. And you can see that you have here 1 hexadecimal digit, and here the other hexadecimal digit. So let's find our 0. Our 0 is right there. So you get the low order first. So you would say, I want the decimal number, which is the 0. Now for the 0, as you can see here, is going to be in hexadecimal 0x. The low order 4 bits is 0, since the 0 is here. So that's the row. And the column is going to be 3. And that's the character that we want. And you can get it for any of the characters. Obviously, if you look here, you'll find special characters. You will find the numbers from 0 to 9. You'll also find capital letters and small letters with some other characters and parentheses, brackets, and so on. Question mark, maybe, and so on. You also have the, I believe this is some of the Japanese letter, because this LCD was made in Japan, I believe, and that's why we have this. Now, so far we said that we have 4 things in the LCD: the data register, the instruction register, the display data RAM or the DDRAM, and the CG ROM. Is that all? No, we have a couple more. We have the character generator RAM or the CG RAM. This is similar to the CG ROM, but it allows you for custom characters. And this is very helpful if, for example, your language is not English nor it's Japanese, it's something else. So if you want to put your own language characters and symbols, you can do that by using the CG RAM. We have also the address counter or the AC. This is you can I mean, you can compare it to the program counter of the microcontroller of any PC. Here we call it an address counter. It stores the current address used in operation that access the DDRAM or the CG RAM, and the AC is automatically incremented, similarly like the PC. It's automatically incremented or decremented after each instruction that writes or read the DDRAM or the CG RAM. Now, usually, if you relate this to the PC is always incremented. Here, it could be incremented or decremented. Now, we said that we have certain instructions, these commands or these instructions. How I can feed these instructions to the LCD? There is a, and this table describe these or the way to feed it to the LCD. We have clear display, return home, entry mode set, display cursor on and off, function set DDRAM address, read busy flags. This is actually a status flag, and read data and write data. These two instructions are the ones that are important, especially the write. So you could say that 90% of the time you are sending data to be displayed in the LCD. Now let's describe each one of them to understand. If you look at the first row here, we have the RS and the RW. And then we have from D0 all the way to D7, which is 8-bit. And we have here the time, which is the time for the instruction to be executed in nanosecond. Now let's look at it. For all of these commands or all of these instructions, you can notice that the RS is equal to 0 for all of them, meaning that they are instructions. And this is exactly what we said in the table when we talked about the interface. Now, the read data and the write data, it's only 1. Now, for the read and the write, it depends on the instruction. Most of them are written, or you are giving the command or the data to the LCD. So either it's a writing the data, or you are giving the instructions to the LCD. Only these two, you are expecting something from the LCD. You are reading to the microcontroller. So we have one here. If you want to read the flags or the status, and one here if you want to read the data. Now, the rest of them is data from D0 and D7. We need certain bit strings to distinguish between these instructions. So for the first one, we said that from D0, from D1 to D7, all zeros, and you have 1 here. If you see this, it means you need to clear the display. If the LCD see this, it understands that it needs to clear its display. Now, return home, if it sees these zeros, followed by this one here, and this bit, it's a don't care. It doesn't matter as long as they are all zeros, and here 1, it knows that it needs to return home. It needs to return the cursor to the home position. Sometimes they call it address 0. It also returns the returns display being shifted to the original position. So the DDRAM contents this way remains unchanged. So what else? We have the entry mode set. In the entry mode set, you have 0, 0, zeros in these bits, and here you have 1. And then you have 2 options, let me sort of speak, or let me say that there are 2 options. You have D0 and D1. D0 is S, and D1 is I/D. So the entry mode set from the name, it's how you are entering the data or the instructions. In the entry mode sets the cursor move direction, either incremented or decremented by using this bit, which specifies to the amount of shifts or the amount of shift in the display. Also, you have the S for the shifting. So you have increment and decrement, and by how much. Display the cursor on and off. If you have this instruction, all zeros, and here you have 1, and you have D, C, and B. D sets the display on or off. C sets the cursor on or off, and B for blinking. Now, more than that, we have the function set. The function sets, if you see of the display receives 0, 0, and here 1, it knows that this is the instruction, and it has the following bits. So you have the DL for the data length. So it sets the interface data length. And N for the number of the display line. It's either going to be 1 line or 2 lines in our case. And F for the character font. So here you'll have only 2 fonts since you have 2 choices, either 0 or 1. Now for the next one, which is set the DDRAM address, if you have 1 here, it knows that this is the instruction. Notice that all of them have 0 and 0 at the beginning. So this is coming for all of them. And the differences, you can see them. Now it says the DDRAM address, and it needs only from bit 0 all the way to bit 6. Now for reading the busy flag and the AC, or the address counter, if the LCD sees 0 followed by 1, then it knows that this is for reading the these flags or the address counter. This is the busy flag, and this is the address counter from 0 to 6. Now for the data, either reading a data or writing a data. 1, 1, you are reading a data, and it gives you the data from 0 to 7. Writing the data, you are writing the data. If you see the LCD sees 0 and followed by 1, or in the most significant 2 bits, followed by the data from 0 all the way to 7. So these are the instruction of the LCD. Now, if you give the LCD a character to display, or you were expecting something from LCD to be read to the microcontroller, you shouldn't expect that it will come to you instantaneously. It needs some times. And we need to worry about these timings. So we have some timing specifications or limits that we need to worry about for the read and also for the write. We will start by explaining the write cycle. You can see that in this table, we have the enable cycle time, the enable pulse width, the enable rise and fall time, the address setup time, the address hold time, the data setup time, and the data hold time. And these are their samples here. And there is, for each one of them, either a minimum number or a maximum number, and the unit in nanosecond. There is sometimes you will see a typical value, but the important part here is the minimum and the maximum. So you don't go below the minimum or exceed the maximum. For all of these timings, for the LCD, the 3 most critical timings are the TAS, which is the address setup time, the BWEH, which is the enable pulse width, and the TDSW, which is the data setup time. These 3 times are the critical timings for the write, and we will find out also the same timings are also critical for the read. Now, it's important to understand for each one of the timers, when does it begin and where does it end? So the TAS for the address, so it starts after whichever comes latest. Usually it's the read/write. So from this timing all the way to the beginning of the enable pulse. You can see the enable here. For the BWEH, it's from the beginning of the enable pulse to the end of the enable pulse. And we have the TDSW overlapped with the timing BWEH. So it is overlapped with it. We know exactly its end, which is the end of the enable, but the beginning is actually when the data becomes valid, the earliest possible time when the valid data start showing up. This is maybe ambiguous, not clear exactly when, depends on exactly where. Sometimes it's a little bit early, sometimes it's a little bit late, but the end is very clear. These are for the timings. Now let's look holistically what's going on here. We have the 3 controls, the RS, the R/W, and we have the enable. The RS, it means its functionality. It shows, is it an instruction or it is a data. If you are writing a data, it's supposed to be, or the bit here should be the appropriate bit based on the table that we described here. So we said if it is 0, then it's an instruction. If it is 1, then it is a data. So it's supposed to be 1 since it is a data. So we have the first control. Since this is a write cycle, the write is low. So you can see that it's 0 here or low. The enable signal here is active high. So whenever it is high, then it is the write is enabled. And as you expected, when you give a sample to write it to the LCD, it won't show up right away. It will take some time, and then after that time, the data or the valid data will show up. Now for the read cycle, we have the same thing here. We have RS, R/W, and E. The only difference here is that R/W here is now high, since it is a read cycle. Also, if you see the comparison between slide 31 and slide 30, if you look closely, you'll see there is many similarities between them. One of the differences is the R/W, obviously, and the other difference is the TDSW, the position of the TDSW. For the write, it's in there or in this region. And for the read, it's in their region. Repeating this in the other slide. This is for the write, and this is for the read. Now, what does that mean for us? For the TAS and the BWEH, same thing, same definitions. For the TDSW here, the timings that we need to worry about here, if you look at the write cycle, you would see these timings, the TAS, the BWEH, and the TDSW, all of them have a minimum value. So this is the minimum that you can accept. Anything less than this is a failure. You won't be able to write the character to the LCD. For the reading, same thing for the BWEH, for the TAS, and for the TDSW. The BWEH and the TAS is similar like the W or the write cycle. It's the same thing here. you have a minimum value. But for the TDSW, now for the read, it has a maximum value. It has a maximum value. What does that mean? For this specific LCD that we chose, you have a maximum of 100 nanosecond. If you exceed that, let's say you have 120 nanosecond, it means you will cause problems for the valid data, which is the critical time here. So you need the maximum to be 100 nanosecond. If it is less than that, the more the merrier, it's better. If it is less, then you will have more time for the valid data. So just be aware of this. For this specific LCD, it has a maximum in the TDSW, but for the write, it has a minimum value. If you look in another LCD and you looked at its data sheet, it might define for the read cycle some timing requirement that resides here instead of here. If the timing is here, then it must be, or it must have a minimum limit instead of the maximum. If you define it here like this one, or this LCD that we chose, then it will have a maximum time. Okay, how to program? Programming is kind of easy because we already explained everything in the previous lecture. For the write cycle code, we will say that these are the control, and in this code, for this specific code, we will assume that RA1 is used for RS, RA2 is used for R/W, and RA3 is used for the enable. If this is the assumption here, you need to go back here and change the connectivity for the E, the R/W, and the RS, and connect them to the right ones, the RA1, the RA2, and the RA3. So just for this code, we chose RS to be RA1, R/W to be RA2, and the enable to be RA3, and the data or the LCD data from RB0 to RB7. This is our assumption for connecting or for programming this code. And you need also to change the data in the interface based on your choice here. Now, for the write cycle, it has two arguments, the data and the RS. The RS to indicate that it is a data, you should give it 1 here. And the data, this is the data that you want to write. So what you do, you configure the trace correctly. So since you have RB0 to RB7 as output, you must have the mask to be 00 here, and the others FF. And then you say trace equal to trace P is equal to trace P and bitwise and with 0x00FF to zero out the first 8 bits to make these ports as outputs, and these or the most significant byte is going to be 1, 1, so it's not going to change. Maybe it's connected to other pins that do other things. Now for the control signals, you have the RS, you put it or you assign it to /RA1, 0 for /RA2, since this is a write operation, and we know that the write have equal to 0, and underscore RA3, which is the enable. You make a sandwich here. You enable by assigning /RA3 equal to 1, and then once you do the writing, you disable or you make the enable inactive. So that's the sandwich, or what I like to call the sandwich. Here, you are writing the data this way. You would say lat B is equal to lat B bitwise with 0x FF00. So you zero out the first byte to prepare it for the data, 0 watt completely, and then you OR it with, or bitwise OR it with the data. Now they let me have the data that you get as an argument. And notice that in the write cycle method, you don't return anything, because since you are giving the LCD a character, you should supply, the microcontroller itself should supply the character in the bus all the way to the GPIOs and then feed it to the LCD. Now, for the read cycle, same definitions here. You can compare slide 33 with slide 32, going back and forth. You see some differences. For the read cycle, the first difference is the trace speed. Now you configure them as input since you are reading here. Before that is actually the arguments. You have only RS. You should give it 1 because you want to read something. And once the read cycle finishes, it should return the data to you. This is why you have a type here, which is unsigned integer 8. Now, to read the data, you prepare the port B in our case, you make it input. And for that, you OR with the flag 0xFF00. The important one is this one. You make it 1 and 1. So if you OR it, you make sure that all of these bits equal to 1, which makes them inputs from RP0 all the way to RP7. The other ones from RB8 all the way to RB15, it's not going to be affected because the mask is 0, 0, and ORing with 0 doesn't change the configuration for RB8 all the way to RB15. Now for the control, and you can compare this to the previous slide quickly. Here we have RS0 and 1. Here we have RS1 and 1. So the only change is here because you are doing a read operation. We have a sandwich. Same thing for the enable. And here when you read from the pins. We use port B. You read from the pins. So port B bit and or the bitwise and with 0xFF00. This way, you take the data from port B, since the LCD already supply it. You are reading. You give it some time based on the timing requirement that we just explained, and you feed it to the pins of the microcontroller. Sorry about this. So now you will have the data equal the port B, bitwise and with 0xFF and 0, 0. So you will have the inputs, which is FF. It will be fed from the port B, since the others will be zeros out, only this one will be available, and you give it as a data, and then you return it. So now this is the way you program. Now, there is a relation between the program and the timing. To understand this better, let's have one of the cycles, which here we chose the write cycle. Now we know the 3 timings that we need to worry about. The TAS is actually after this instruction, which is underscore RA2 equal to 0, and that's for the read and write. So from the beginning of the read and write, exactly at the end of this instruction, this corresponds to the beginning of the TAS. The end of the next instruction, which is the underscore RA3 equal to 1, and we know that the RA3 is the enable. So the beginning of the enable is the end of the TAS, and this is exactly how you map the code to the timing that you need to worry about, which is the TAS. Now for the PWEH is basically the sandwich from the end of this instruction to the end of the next, or for the end of this one. So this is the end, or this is the beginning of the enable, and this is the end of the enable. And this will be the timing period of the BWH. Now for the TDSW, it's actually from the end of this instruction. When you're done with this statement, it means that the data started to be valid in the bus. So now the beginning of the TDSW is going to be the end of this instruction, and the end is the end of the enable. Now, since we understand each instruction and how is it affecting the timing, we know that we can calculate this time if we know how much time this instruction needs to execute. For the TDSW, we can understand this timing or calculate this time if we find out how much time this instruction needs to execute. For the others, or for the BWEH, it's actually for these two instructions together, this one and this. Now, how much time an instruction needs to execute? We explained this previously in one of the lectures that we talked about, and it's very tied to the frequency of oscillation. If you get the frequency of oscillation, you can get the frequency of instruction cycles by dividing that by 2. And to understand this better, let's have this example. In this problem, you are given a processor with a frequency of oscillation 80 megahertz, and you were asked to draw the LCD signal for the write cycle. So now we are talking about a write cycle. You can practice yourself for read cycle. Now assume each statement, the C statements, execute in one instruction cycle. So actually, by this assumption, we are making a one-to-one mapping between the high-level language, the C language, and the assembly code. Also check whether the parameter, the TAS, the BWH, and the TDSW, which are the 3 timings that we talked about, check if they are met, or the timing requirement, or the timing limits are met or not. If they are not met, then modify the code to satisfy the parameter. How to modify the code? We are actually will delay the code a little bit more by using no operation. How to do this? This is the solution. Each statement takes 1 over 40 megahertz. The frequency of oscillation here is 80 megahertz. So the FCY is going to be FOSC divided by 2, which is going to be 40 megahertz. Now you take the reciprocal for this one to get the time, which is 25 nanoseconds. Now from the previous write cycle that we showed to you, the TAS minimum value, or all of them actually have minimum values. So the TAS is 30 nanosecond, the TDSW is 40 nanosecond, and the BWH is 150 nanosecond in the table. Now, you will see from here that the TAS have 25 nanoseconds since it needs 1 instruction. The TDSW is 25 nanosecond, 1 instruction, and the BWH is 2 instruction, which is 50 nanosecond. This is exactly what we explained in the previous slide. So the minimum is 30 nanosecond for the TAS, but it is 25 nanosecond here. So it's not met. The timing is not met. We need to prolong the time of the TAS, add something to it. The BWH is 150, and this is really terrible. It's not met at all. It's only 50 nanosecond. The minimum is 150. And for the TDSW, it's also 25 nanosecond, and the minimum is 40, so the timing also is not. How to solve this? We can slow down or delay the signals by adding knob operation instructions. Since they are instructions, each knob will also need 25 nanoseconds. So each knob will also increase the time by 25 nanosecond. How to work this out? We show this in this slide. You can see that the code after the modification will be like this. Since this is the timing before the code modification, the one that we just saw, we know that the minimum is 30, so we will add one knob operation here to make the 25, 50 nanosecond. To add this knob, we add it right here. Because this is the timing for the TAS from the end of this instruction to the end of this instruction, as we explained. Okay, for the PWH, it's only 50 nanosecond. So we need 4 knob operations or 4 knob statements to make the 50 nanosecond 150, since each one of them is 25. So 25 plus 25 plus 25 plus 25, that's 100, plus this 50 becomes 150. So you need 4 knobs. Initially, we make the 4 knobs right after activating the enable. So we put knob, 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 and another knob. So that's initially we put the knobs right there. And then we worry about the TDSW. The TDSW is 25 nanosecond, and we need to make it more than 40 because that was the limit. So we add one knob for the TDSW to make the 25 nanosecond 50 nanosecond. Now, since there is an overlapping between the BWH and the TDSW, now what we can do is we move one of these knobs right into the period or the space for the TDSW timing, which is the end of this instruction to the end of this instruction. So we put it right here. So at that point, for the enables, you have 4 knobs, and for the TDSW, you have 1 knob, and you can see the overlapping here. So this way, by adding 1, 2, 3, 4, 5 knobs, you fixed the timing requirement. So you always have the same code. The only difference is adding the knobs. Is that the only way to do it? No, there are so many other ways. That's only one way of doing it, delaying by the knob operation. You could have a delay function that you can give a specific amount of delay for it. There are other means as well. Now, at this point, we finished interfacing and programming the LCD. And for the next time, we will talk about another module of the Big 24, and we chose the timers because it's easy to manage, and it's also a very critical module. And this is what we are going to discuss next time.